All right. Gonna get started here in a second. Let me just move some stuff around on the desktop here. Move that. Can't close this countdown program. Won't need that. What's this? That can stay open. Okay. Sorry, I just had a million windows open on my desktop there. I had to sort out what was going on. All right. So let's go ahead and get started here. All right. So I only have 3 problems here, so it'll probably be a little bit short today. I wanted to keep it simple in case things got a little bit long. But let's go ahead and get started. So problem 1 here. We have a force of 250 newtons stretches a spring 30 centimeters. How much work is done in stretching the spring from 20 to 50 centimeters? So this is where we're going to use the force being Hooke's law. Okay. So F equals kx. Right? And here, we need to figure out what the spring constant is. Right? So a force of 250 newtons is stretching the spring 30 centimeters. So plugging that stuff in here, we have 250 newtons is k times, now 30 centimeters is 0.3 meters. Okay. So this is going to tell us that, let's just do it on the next line. This is going to tell us that k is going to be 250 over 0.3 newtons per meter. Okay. And let's see, if we, this is going to be some decimal, isn't it? Let's see, 250 divided by 0.3. It sure is. So let's just do this. Let's write it as 2,500 over 3 newtons per meter. So multiply the top and bottom by 10 to get rid of the decimal. And then we'll do the final approximation at the end here. All right, so here's our value of k. So the question then is, well, to find the work done, I need to integrate this force function. Right, so 2,500 over 3 x dx. Right. The question is, what are the bounds on this integral? Well, we're stretching the spring from 20 centimeters to 30 centimeters. Oh, you know what I didn't do? No, this is fine. This is fine. We don't need to know the natural length here because the force stretches at 30 centimeters. And I think this is maybe worded a bit odd here. But we're going to stretch the spring from a stretched length of 20 centimeters. So it's stretched 20 centimeters already beyond its natural length. We're going to stretch it an additional 30. Okay. So here, this will go from 0.2 to 0.5. Right? So from 20 centimeters to 50 centimeters. And we have to convert these to decimals because this needs to be in meters because of the newtons here. All right. So, do our integral here. This will be 1,250 over 3 x squared from 0.2 to 0.5. And let's see, what do we get here? The 2050. Sorry. 1,250 over 3 times 0.5 squared, 0.2 squared. 1,250 over 3. I don't know where all those sneezes came from. Right, so it's 0.25 minus 0.04. So this is 1250 times 0.21. Divide that by 3. And so here we get that we've done 87.5. And again, this is going to measure in joules. Right, we set everything up so that this measures in joules here. So that's the amount of work done to stretch the spring from a position of 20 centimeters away from natural length to a position of 50 centimeters. Again, the problems may be worded a little bit odd, but this is what tension is. Okay. So let's look at problem 2 here. Now this one I haven't actually done beforehand or looked up the solution to or anything like that, so let's hope we can get it. Alright, so in problem 2, this shouldn't be too bad though. Right, we have a hemispherical tank of radius 6 feet positioned so that its base is circular. Right? How much work is required to fill the tank with water through a hole in the base when the water source is at the base? So what do we have here is we basically have, here's our hemispherical tank. Okay. Come on. Yep. So there's our tank here. And our water source is here. Right, so let's say it's in the center, it doesn't really matter. Right, and the water is filling it up. Something like this. It's probably not spouting out like that. That would be a different thing. But we're just filling it up from the bottom. Maybe I don't want to make it that. Okay, so it's filling in from here, from the bottom of the tank. And so that water level is going to rise through the hemisphere. Right? So the radius of this tank is 6 feet. 6 feet. Okay. So here, since the water is being pumped in from the bottom, you might remember we did this one about draining a draining a conical tank by pumping the water out of the top. There we were pulling the water from out of the tank upward. Here we're sort of pushing stuff in from the bottom. So it'll be a good idea to measure x going this way. So we're going to say here is 0, right? And then we move upward. So we're going to do basically the same kind of thing we did last time to try and figure out the work done here. So let's see. So what we have to do then is say, all right, well, let's take sort of a cylindrical chunk here. Right, we want to take a cylindrical chunk of this sphere. Right, we're going to say this has thickness delta x. Okay, and then somewhere in the middle here, we're going to say, okay, this is at height xi star. All right. So what we want to ask is basically, how much work was done to push the water up to that point. All right. So let's see here. So what do we need to figure out? We need to figure out the volume of that slice, which means we need to know the radius at this height. So here we have, this is a hemisphere of radius 6. So the equation sort of for the radius here, right, we can say, let's see. We can say here that the radius squared plus sort of this component, so xi squared, xi star squared, call this ri, this has to be 6 squared. All right. So how is that kind of working here? Maybe I should explain that a little bit better. Let's see here. What's the So the equation of the sphere is x squared plus y squared. Using regular coordinates here is a bit odd. All right, so let's do this as an aside here. So the equation of a sphere is x squared plus y squared plus z squared equals, in this case, it's going to be 6 squared, so 36. This is the sphere of radius 6. So, essentially, if I'm trying to measure, here's my sphere, and let's say I want to take the radius of this part right here. Right? But here, I want to think of like, what is this distance here? Well, this is a circle that's kind of parallel to the x and y directions, because this is the z direction. So if I just put in whatever z value I'm at here, that's going to turn this into a number. And then this part right here, so let's say, this is going to be x squared plus y squared. And this will be 36 minus z squared. So whatever number this is, that's actually going to tell you the radius, or the square of the radius here. So this r value, this is r squared here. Right? So that's what I'm using. Right? So here we can say ri squared plus xi star squared. This has got to equal 36. So the radius is going to be square root of 36 minus xi star squared. All right, so we're looking at this here. Okay. So that means the volume of this part, VI, is going to be pi ri squared delta x. Okay. And so this is going to be pi ri squared, so we just have 36 minus xi star squared delta x. So that's the volume of this part, of that shell. Or sorry, that slice. Okay? And then we're saying, well, how much work has been done to push that sort of cylinder of water up that high? So we have to get to that. So to get to the work done to do that, well, this is the volume. What we need is the weight of that water, right? Because work is force times distance. So in this case, the force, again, that we're kind of fighting is the force due to gravity. So if we find out the weight, which is, in essence, the force due to gravity, we can take that and multiply it by the distance traveled. So what is the weight? Well, first, to get the weight, we need to do we need to find the mass. Mass is volume times density. So mass will be volume times density. Right? The density of water is what is it in these units? Let's see. Okay. I need to find this in the right units. All right, you know what? I'm just going to leave it as rho for now. All right, so this is just some number anyway. So that's the mass. It's going to be pi times rho times 36 minus xi star squared delta x. I'll find this number in a second. So now that we have the mass, we need to find the weight. Okay? So the weight, which is going to be the force in this case, it's mass times acceleration, right? Just Newton's law. So here it's the mass of the ith part times g. So this is, pi rho. We may as well just leave all these as constants for now. 36 minus xi star squared delta x. And so the work being done on this part to lift this part up, right, is going to be the force times the distance traveled, right? The distance we lifted it up, which is, since we're doing approximations here, we can approximate that we've lifted up this cylinder of water by a height of xi star. All right. So that means that the total work that we want to do is going to be the integral of fi times xi star. Well, we're going to replace these stars with xi stars with just an x, delta x with a dx. And we're going to get pi rho g 36 minus x squared times x dx. Right? Now, what are the bounds on this integral? Well, the question is, what is the very top of this? How high is the very top? Well, it's a sphere, so if this is 6 feet, then all the way from the center to the top is also 6 feet. So we're pumping water from the 0 all the way until this fills up. So we integrate from 0 to 6. Right? Okay, so let's compute this integral. We're going to get, I'm going to factor out all these constants here. And then let's multiply this out. 36x minus x cubed x. So pi rho g, this is going to be 18x squared minus 1/4 x to the 4th from 0 to 6. Pi rho g, let's see, what do we get? 18 times 6, 648, 6 to the 4th, divide by 4, minus 324. Oh, that's interesting. Okay, so this is going to be 324 pi rho g. Right, and this should measure in foot-pounds here because of our units. So let's make sure we get these units in here, right? So 324 pi. G is going to be 32. G is going to be 32 in this case, right? Because in imperial units, the acceleration due to gravity, well, this is approximate. It's approximately 32 feet per second squared. All right, let me double check that, but imperial units are awful. Okay, yeah, it's about 32 feet per second. So we'll just use that. And actually, let's do this. Call this one 32. And then we need rho. So I still need the density of water. So I want this in pounds per cubic feet. So in pounds per cubic feet, the density of water is 62.4. Right, so this will be in foot pounds. See, here's another reason that imperial units are terrible. Because if we did this in SI units, in kilograms per cubic meter, it's 1,000. It's just that much better. But anyway, so let's see, times 62.4 times 32 times I on here. Okay. So it is about 2.03 times 10 to the 6 foot-pounds of work. Okay. All right. Oops. All right. Any question there? Yeah, so fun problem, this one here. I always enjoy these, sort of figuring out, like, how we have to set this up. And these are kind of neat compared to just normal integral problems, because we sort of have to, like, recreate the integral each time. We have to, like, rebuild a Riemann sum almost. And so it causes us to really think about, like, what are we really doing in this process, right? It's not just a generic, hey, here's some, integral, compute that. Okay, so that's it for that question. Now the last question here. Yeah, so we've spent 30 minutes to do 2 questions. All right, so the last question here is, we have a cable which is 60 feet long, weighs 180 pounds, and it's hanging from a crane. So what do we have? Let's say here is a crane. And from the top of this crane, we have a cable, probably some spool up here so it can attach to, and then it's a cable that's just hanging down. All right, and let's see. This is a 60-foot long cable, and it weighs 180 pounds. We want to find the work done if the winch at the end of this crane here pulls up 25 feet of it. Okay? So this is another case where we want to measure 0 at the top and 60 at the bottom. And the reason we want to do that is the cable is moving up this way. So we want to use this axis here to say how much cable is left. Okay? It'll be a lot easier that way. Right? So let's look at, how much work all this should take. So let's see here. We want to right. So we want to find the weight per foot. So if this cable weighs 180 pounds and there's 60 feet of it, not 6 feet, 60 feet, then this is going to be 3 pounds per foot. So what we want to do here is say, okay, if I focus on this little chunk of the cable here, this little delta X of the cable, okay, And let's take a sample height in here, xi star. If I focus on this chunk of the cable, how much work does it take to raise that bit of the cable up to the top? Okay. So, how do we do this? Well, what we're going to do is say, let's see here. So we need to find the weight of this segment and then how far it gets pulled up. So here. So let me think carefully about this because we're not pulling it all the way up. Okay. Think about this a little more. I had an answer in mind for what this was. I didn't think it very carefully. Well, anyway, let's look at the weight of this segment. So the weight here, maybe I shouldn't call it I. The force on this part is still going to be 3 delta x. Because this little segment, the weight of that is this length times how, times this sort of density. Density. So I think we have to do this in 2 pieces, actually. Oh. So let's see what's going on in this problem here. So we're lifting all of this cable up 25 feet. So the first 25 feet of this cable get wound all the way up, right? And so the work, so for the first 25 feet cable, the work is going to be the integral from 0 to 25 of force times distance. Force times distance. The distance is the entire x. So 3x dx. Let's call this work 1. Right? Because the entirety of that length is being pulled up. Now for the rest of it, it's not getting pulled all the way. So from 25 feet onward, right? This part is being pulled up a distance of just 25 feet. So it's not 3 times x because the distance isn't changing. Every bit of this cable from 25 feet downward is being pulled up a distance of xi, or of 25. Right, so it's going to be 3 times 5. Right, so the x here gets replaced with 25 down here because, again, it's not actually that distance isn't variable in this case. And then here we need to integrate that from 25 feet to 60 feet. Right? So the total work done will be the sum of these two. Total work is going to be the integral from 0 to 25 of 3x dx plus the integral from 25 to 60 of 75 dx. So let's compute these. This will be 3 halves x squared, 0 to 25, plus 75x from 25 to 60. This is this is 937.5 plus 35 times 75, 2065. Add these two together. We have 3,562.5. And again here, this measures in foot-pounds. That's the have. Okay. So, any question at all here? Yeah, so it's an interesting problem here to think about. Yeah, like I was saying, when I first looked at this one, I thought there was going to do it. And as we start doing it, get a little more interesting. That's kind of why I like just picking problems and not sort of at the end. Because if I have to think through it, you can kind of see my process for sort of help. So, there are no questions. Be it for today. Good afternoon.